Okay, I want to go through your multicast example that's in the course example code. These are very straightforward, simple examples um, that you can run. There's a basic sender, a basic listener, and then a multicast peer that will both first listen or send a message, I should say, and then listen. These are going to use the calls to join a group. They're going to use the calls to send and receive messages over UDP. So on the top, we have the sender. Straightforward parsing command line argument. We have to give it a message. We have to give it the address. Notice the nature of the address that by default up here, we'll just use that one, 228.5.6.7. We're not using loopback. We're not using the local host, right? We're using that virtual IP address as we were talking about in the lecture. Um, After it processes the command line arguments, it goes and gets the internet address. It goes and gets the, I'm sure my bad indentation there. It creates a multicast socket at that port, and then the socket has to join the INET address group for that. So that we didn't see that in the other socket-based programs. Then we create a datagram packet because we're UDP based. We send the packet, leave the group, close. That's all that the sender's doing. It's going to send something, and then it's going to leave. Now, of course, if I have the sender all set to go up here in this window, when I go ahead and hit the sender just returns, right? We didn't see anything in the other windows because I'm not running any listeners yet, right? If I start up the listener that I'll talk about next, it'll be waiting for a multicast message, but it didn't get the one that I just sent, right? It's not held on to for the destination. I mean, it's fire and forget. It fires off the message the sender doesn't care whether it came back or not. There's no acknowledgement, and it just completes, right? And when the listener comes up, there's nothing waiting for it. Nothing sits there and queues anything up. There's nothing, no magic going on between the scenes. So anyway, let's go back and talk about the listener here for a second. The listener is going to do similar logic, parse its command line arguments. In this case, the listener is also going to take the address and port. It's not sending a message, so it doesn't have that on the command line. But similar kind of logic here, right? We have the group for the INET address. We have the multicast socket. We join the group. Now we're going to those set up so that we can receive, and we're receiving in a do while loop. That we get, right? So um, the while goes until we get a special message stop. Otherwise, it's going to sit there and wait for a multicast message until we're done and print that message out to the screen. So a very simple receive of a string over a datagram. Notice how we're not really worrying about any of the UDP concerns for quality of service or anything because we're sending a simple message. We're assuming the datagram is going to be small enough. It's going to be or the message is going to be small enough to fit in a single datagram. We're not going to worry about the sequencing or anything else like that. But also notice how even though it's a string, we are getting it in a binary buffer, right, via datagram packet. We don't have any typing information. We're not hooking up streams, input and output streams like we do with the TCP socket. We're getting that array of bytes in the message and then converting it to a string, right? That's what the new string call is right here. So anyway, now if I start up the listener first, and I go ahead and I send a message via the sender, right? I get hello. And notice how it's still waiting for a multicast message. I can go over here and type stop, for example. And I stop, and because I got that message on this side, the listener actually exits this time. All right. Then the third program we have is a multicast peer. The multicast peer, by the way, is really just doing the combination of the two. All right, same thing, command line. It's going to take on its command line arguments, just like the sender, a message, an address, and a port, and same kind of logic that we saw before. It's going to have a group. It's going to join that group. It's going to create a multicast socket. It's setting up for both the send and receive, though, right? So we have a message out, the outgoing message that we're going to send, but then we're also going to, in a for loop, receive messages. So this one's going to keep executing until we receive, let's see, the loop is from 0 to 3. So it'll receive 3 messages and then exit. So I can run this one at the same time. Notice how it sent a message first, right? So it sent and received it. It's printing out received, but it also sent it, right? So it received its own message because it was acting as both sending and receiver. Now the listener's starting after this message was sent, so it doesn't see it. Now again, if I want to do that again and now start the peer after the fact, right? Now both of them receive yo, both the listener and the peer itself, okay? Now both of these bottom 2 windows are listening. The sender can also send another message. We'll send hello again. and notice how both of them get the message. So everybody in the group is getting the message, and I can do that a number of times. I can ask the listener to stop, and the multicast peer stops as well. Okay, so that's how very straightforward UDP working in a group type of message. Again, maybe perhaps some limited applications for which this makes sense, but very interesting functionality that you can conceive, and certainly more efficient than us taking the sender and having the sender trying to manage individual sockets, right? At this point, if the sender had to, think of what the sender would have to do if I go back to this code right here and make it larger. Right now the sender is just sending out a particular address. It's fire and forgetting, it doesn't have to worry about it. If I had multiple clients that wanted to connect to the sender to get individual sockets connections to receive the message that it's sending, then then in our TCP world, if you remember, we would have to accept and actually get into multi-threading to allow multiple clients to join and send the messages individually. So certainly we could do it, but it wouldn't be as efficient right here, right? From the sender's perspective, it puts a message on the wire. Also notice that the sender is completely decoupled from any notion of how many listeners are out there. I could have brought up as many listener windows as I wanted and run them all, and they all would have received the message. And the sender doesn't have to know. So the sender is decoupled from how many clients are out as well. So there are some interesting efficiencies with this approach.